In this lesson, we are going to be talking about rules of differentiation. So this is the beginning of derivatives, and we're going to be doing some shortcuts. There's a bunch of different rules to creating these derivatives. We're not going to be doing a limit or anything like that anymore because they're shortcuts. So remember that when you're talking about a derivative, you're talking about finding a slope. So we're going to be taking some sort of an equation and we're going to find its slope equation. So here's the original equation and it has a particular graph, but then there's also a slope equation to it. And that's kind of the goal on all of these. So just some terminology just to make sure we're okay with. When you do a derivative of a function, you're going to be doing like an f prime, and that little symbol right there represents that we've taken the derivative. This is a y prime, dy dx is another way to represent it. This is an operation. We're going to be doing the derivative with respect to x. So that look right there. So we're doing the derivative of this with respect to x. So let's get into it. So a constant. So if you have a constant, so if C is a real number, right, then the derivative with respect to x of a constant is 0. And if you think about visually, if you're talking about some sort of a y equals 5, right, and your graph looks like this, and this equation of y equals 5 is just a constant. It remains at 5. Well, what's the slope of that line? The slope of that line is 0, right? So the derivative, which is the slope of any constant, is 0, right? So there's always kind of a visualization that you might be able to connect it to. And then here's where we get into the majority of them. So if we're talking about the derivative with respect to x of some sort of an equation that has a power to it, to do this derivative, we are going to bring the power down, and then we're going to subtract a power. And that is something we're going to be doing over and over and over and over again. So, for example, if we're doing the derivative of this, the answer is we bring the power down and we subtract a power. So the derivative, the slope equation of this equation, would be 9x to the 8. Right? And then here we have a power of 1 if you need to sneak that on. And so it would be a 1x to the 0, but anything to the 0 is 1. And if you visualize this and you think about what does that graph look like, it's just 45. And what's the slope on this? So if you go from point to point, you would be going up 1 over 1. So the slope remains constant at 1. It doesn't change. All right, so a little bit of a visualization to it. And then here, we're doing the derivative of this. Just because as a power does not mean that it's a variable raised to a power. This is actually a constant. And so the constant, what's the slope on a constant? The slope is 0. All right, so if you have a constant multiple rule, which means if you were going to take the derivative of some function that has a value multiplied to it, then you can actually take that value out and then do the derivative of it. All right, it may be helpful, it may not be helpful. For example, you have something like this. You can take this -7/8 out if you would like, but you don't have to. So let me kind of show you what I mean by that. We can take that -7/8. So let me rewrite this just so you can see it a little bit better. That we could write this as a -7/8 times x to the 11th, right? And so then that would allow you to take this multiple out, and then we can go ahead and do the derivative of x to the 11th. Now you don't have to do that by any means. You could just basically bring that in. Well, we'll go through in just a second. So we have our -7/8. We do the derivative of this. We're going to be multiplying it by, we bring the power down, 11 x to the 10th. And if you smush it all back together, you're looking at a -77 over 8x to the 10th. Right, so that's one way to do it. Or you really could just bring that in front, multiply it to the 7, drop your power down. Right, that's probably the shortcut that I would do. I wouldn't necessarily break this up. It usually is not all that beneficial. So let me show you not doing that on this one. So first thing I do want to do though on this one is square roots. We want to rewrite those. And so if I have that, let me rewrite that as 3/8 x to the 1/2 power. Then that's easier now to bring your power in front and subtract your power. So if we do that derivative, we're going to be doing 3/8 times power is going to come in front. It's going to come down and we'll subtract a power. So we're taking a 1/2 minus 1, which is going to get us a negative 1/2. Right? And so if I mix all this stuff together, we're looking at a 3/16 x to the negative 1/2 power, which also could be rewritten as this is a negative exponent. So I could bring that negative exponent down and join the 16, and the 1/2 power is a square root. So a lot of times if the original problem starts as a square root, we want to, or a root of some kind, then we want to bring our final answer back into a root of some kind. That's usually how this works, but technically this isn't wrong. Just kind of depends on what we're looking to simplify it into. And then we'll do one last piece here, that if you have a sum rule, which basically means if you have the derivative of some function or a piece plus another piece, right? They're these independent values. Then really all you're doing is the derivative of each. Right, so which really means I can do the derivative of that, derivative of that, derivative of that, derivative of that, all kind of independent of each other. So if I do that, I'm doing the derivative of this, power is going to come down and multiply to the 2, which makes it a 6. We drop the power down by 1, multiply, so that would become an 18 w to the first. Right, I can put a 1 on it, but I don't have to. And then minus 6. This is going to keep it as a 6, but this would become a w to the 0. And so I don't need to write that. It's not, again, not wrong. But then we're back at the end here. So let me just write it one time. And then the derivative of a constant would be 0. So if we clean that up, we're looking at 6w to the second plus 18w minus 6. And that would be our final answer on that. Right, and so you'll get used to, the more you do these, of derivatives of constants just go away. Derivatives of linears versus quadratics and cubics, derivatives of linears just become the constant in the front, the coefficient, right? Because that's always going to drop to a w to the 0 or an x to the 0, which is going to go away because anything to the 0 is just a 1, right? So you get used to that as we go through it. All right, and that was just a brief introduction to some of the rules, the very beginning of the rules, especially the power rule on individual problems.